Hello and welcome to lecture 3 of week 9 of the course Introduction to General Relativity. Just like the previous lecture, this lecture is approximately 1 hour duration and will be split into 2 lectures on the NPTEL website. In this lecture, we will look at general relativity in the weak gravity or weak field limit, so-called linearized general relativity, and the gravitational wave solutions which emerge in this regime. Alright, the references for this lecture and the next lecture on gravitational radiation are as follows. Carroll's lecture notes, chapter 6, almost entirely. Ohanian and Rufinian's book, 3rd edition, I'm using. Chapters 4 and 5 will contain the relevant material. And as usual, for every lecture notes will be posted on the NPTEL/Prime website. So let's look at the agenda for today. First, I'm going to look at this weak field limit of general relativity, so-called linearized general relativity. And we will see that this turns out to be the same as Fierz-Pauli theory. Then we're going to study vacuum solutions in this linearized theory, and we will see that these solutions are the form of gravitational waves. In particular, we will look at gravitational plane waves. We will spend some time in studying gravitational plane waves, which is realized when you have gravitational waves far away from the source emitting the gravitational wave. Alright, let's start with the weak field approximation of linearized GR. First, some motivation. Einstein field equations are nonlinear and extremely hard to solve, and we can simplify it in the weak field limit in which gravity is weak, and the metric can be considered to be a small perturbation around Minkowski space. So here's the metric, and we've written it in the form of a perturbation around Minkowski space. So the metric is larger than Minkowski, and on top of that there's a minor perturbation or small perturbation. This metric perturbation I'm denoted by h mu. As you can see, it's a perturbation because its components, or the magnitude of the h mu, is much less than 1. Minkowski metric components are order 1, and the metric perturbation components have magnitude much less than 1. As a result, all general relativistic quantities such as connections, curvature, etc. have to be expanded in this metric perturbation to leading order. And often it will turn out to be linear order. The leading order will turn out to be the linear order. Okay? And also when we raise and lower indices, we will raise using eta mu, because if we include this metric perturbation, it will contribute to a term which is of sub-leading order. And we are supposed to restrict ourselves only to leading order. So, raise and lower indices purely using the Minkowski metric. The metric inverse, once we have this metric in the form of perturbation, we can compute the inverse, and to leading order you can show that it is equal to this Minkowski metric inverse minus h mu with mu indices raised. That means h mu, which is obtained by raising the 2 indices with the Minkowski metric. Eta alpha mu, and then eta beta nu times h alpha beta. Okay, these are etas. I'm sorry about the writing. So the metric inverse leading order looks like this. We will drop the second order term. Levitard's connection, which is given by this formula, turns out to be again linear in h. In particular, it's linear in h, and first order is a derivative. And then there are higher order corrections, which is wrong, because we're looking at the leading order theory. The Riemann curvature tensor, which is given by this formula, also works out to be linear in h, but second order in space-time derivative. Okay? And then as usual, we will drop the higher order terms. The Ricci tensor, which is obtained as contractions of the Riemann tensor, again is given in the linearized approximation by a linear order expression in h, which is also second order in space-time derivatives. So because of this contraction, I have to introduce this quantity h, which is the metric perturbation with its indices contracted by the Minkowski tensor. Okay, so this is like the trace of the metric perturbation. The Ricci scalar makes us having to take another trace So in this case, we obtain the linearized version of the VT scalar, which is with various indices contracted. Finally, the Einstein tensor, which appears in the field equation in linearized approximation, something like this. Again, the main feature is that it's linear in the metric perturbation and contains second order, contains two space-time derivatives. So Einstein field equation, indeed, it simplifies the linearized limit to a linear equation. That's why we call it linearized GR. And if you look at the equation closely, you should be able to identify that this is nothing but the Fierz-Pauli equation, which you learned a long time back in special relativity. So in linearized approximation of the weak field regime, Einstein general relativity reduces to Fierz-Pauli theory. Okay, of course, the way of writing metric as Minkowski metric plus a small perturbation is not unique. And in fact, if you perform a small diffeomorphism or gauge general coordinate transformation, then you can show that the new metric can still be written as Minkowski plus a small perturbation, but the form of the perturbation will be different from H nu. So the new metric, after performing this small gauge transformation or coordinate transformation, can be written as Minkowski plus small perturbation. That's right. It's different from H. They are related by this force. Okay. So treating H and lambda of same order, all these terms are of higher order, we will drop. The two versions of the famous Fierz-Pauli gauge symmetry, which you had learned earlier in special relativity. And you can also check, we do this check, that if you plug H prime instead of H in the definition for the Riemann tensor, you get the same Riemann tensor. Okay? So in this Riemann tensor, if you compute using H or using H prime, then you get the same answer. So it's invariant under these kinds of gauge transformations, the Riemann tensor. Okay? They will lead to the same Riemann tensor. So because H is non-unique, in order to solve the equation uniquely, we need to fix a gauge. Okay? Choose a particular coordinate system. And the preferred coordinate system which is used is called the Lorentz gauge. People call it the Einstein gauge or the Hilbert gauge, or more popularly the de Donder gauge. In many papers you will find the de Donder gauge or even Fock gauge. Okay? So that is given by this condition that since the Einstein field equation will not determine the metric uniquely because there's a lot of ambiguity going to gauge transformations, we will choose a particular coordinate system or gauge transformation in which the metric perturbation should satisfy this equation, which is called the Lorentz gauge. Okay, so these gauge conditions, Lorentz gauge conditions, can be used to eliminate or fix D components of the metric perturbation. Remember, I'm going to work in big D space-time dimensions. I'm going to keep an open mind and not choose D to be equal to 4. So D is general or arbitrary and not equal to 4. Of course, we will especially treat the D equals 4 case. But in general, throughout, I'm going to use the space-time dimension to be D, which is arbitrary. Okay? So in such case, H nu being a symmetric tensor in which mu can take D different values and nu can take D different values, total number of components of such a symmetric object will be D times D plus 1 over 2. But these are not all of them are independent or free because they have to satisfy the Lorentz gauge condition, which, as you can see, is a vector condition because the index mu is dummy, but the index nu is free. So for each different value of nu from 1 to D, from 0 to D minus 1 or 1 to D, you'll get an extra constraint. So there are D constraints which can be used to fix or eliminate some of the components of H nu. So the number of components which are killed by the Lorentz gauge must be subtracted. So this is equal to E times E minus 1 over 2, this difference. Alright. So if you put the Lorentz gauge, the Einstein field equation in the linearized GR or the Fierz-Pauli equation simplified, sorry, wave equation with a source. Okay, so box, this is the wave operator, most of you remember, the D'Alembert, which is the wave operator. So the wave operator acting on h bar mu, which I will define in a second, is equal to some source, matter energy source. Okay, so this h bar mu, which is defined by this combination, h mu minus half eta mu times the trace wedge, is called the trace reverse matrix perturbation. Because if you compute the trace, that is, we contract with eta mu, it will turn out to be minus of h, minus of the metric trace of the metric perturbation. So since its trace is negative of the metric perturbation, this is called the trace reverse perturbation. H bar is called the trace reverse perturbation. Alright, so in the simplified limit, we can look at solutions for vacuum, that is outside sources. That is, we set T mu equal to 0 on the right hand side, and we get the normal wave equation. Okay, so H mu satisfies the H bar mu satisfies the wave equation, but the H bar mu are not all independent because there is, of course, the Lorentz gauge condition. So the Lorentz gauge condition also simplifies in this using this trace reverse perturbation. It becomes just 4 divergence of the trace reverse perturbation vanishing. And the solutions of this wave equations are non-dispersive transverse waves which propagate at the speed of light. Of course, because the D'Alembert operator appears here, that means these waves are going to propagate with the speed of light, and these waves are called gravitational waves. Okay. So the number of polarizations in this calculation we already looked at in the last slide. This is the total number of components of H bar mu, and we have to subtract the number of Lorentz gauge contained in this. However, this is not all, because not the full story, because Lorentz gauge is only an incomplete, is a partial gauge fix. It does not determine the metric perturbation uniquely. Okay, you can still perform a general Fourier transformation, x going to x prime, which is x minus chi, such that this chi satisfy the harmonic gauge condition, which is box of chi vanishing for each component of chi. Remember, chi is a vector field, okay? Because as you can see, x is a vector, x prime is a vector, x is a vector, and hence chi is also a vector. So they're D independent functions. And if I perform a general Fourier transformation like this, then of course Lorentz gauge condition shifts because the nearest nu will have an extra piece. But if this extra piece vanishes, that is, if we choose the x chi nu's to be harmonic functions which satisfy box of chi nu equal to 0, then h bar prime also satisfies the Lorentz gauge. So in the same gauge, we have two different metrics, so that means the gauge is not good. It has only partially determined the metric component. This is not going to be able to determine the metric component uniquely. Okay, so we can still, because we still have freedom to perform gauge transformations or Fourier transformations. Now, we can use this residual gauge transformation. So this transformation using harmonic functions is called the residual gauge transformation, or Fourier transformation symmetry, to kill off some components, kill off or determine some of the components of H nu and how many D. Because X chi nu is a vector field, so it has D independent components. So this will give me, this condition will, can be used, this ambiguity can be used to determine D components of H nu. So then the total number of polarizations of gravitational waves, that is independent degrees of freedom, is, this is something which we started with. This is just the symmetric number of components of a symmetric tensor. And then Lorentz gauge takes away a D, and the residual gauge takes a further d components. So if you do the math, this turns out to be this number, d times d minus 3 by 2. Okay, so in big D dimensions, the number of gravitational wave polarizations is given by this number. Okay, now you can plug in d equals 4 and check that this gives you 2. So this number will turn out to be equal to 2. So in 4 dimensions, which is our world, there are 2 gravitational wave polarizations, and this is very similar to the electromagnetic wave. We know in 4 dimensions, the electromagnetic wave also has 2 polarizations. But the similarity stops in 4 dimensions itself. If you go to arbitrary dimensions, the number of gravitational wave polarizations is d times d minus 3 by 2, while the number of electromagnetic wave polarizations will always be d minus 2. So they're not different. They're not same in general. Only in 4 dimensions there is a happy coincidence. So since I've already brought up this issue of electromagnetic waves, let's pursue this comparison of gravitational waves with electromagnetic waves further. It's instructed to do that. So remember, what this would actually call the Maxwell equation, which is this. And if I write the Maxwell equation instead in terms of field strength, in terms of potential, the Maxwell equation looks something like this. And in Maxwell equation, we are already familiar with the fact that there is a gauge redundancy. That is, the potential is not unique. In fact, I can change the potential by 4 divergence of an arbitrary scalar field, lambda of x, little lambda of x. Then we get a new gauge potential, which is also a solution and in fact represents the same electromagnetic field. So the F mu nu computed from A or A prime will be the same. So they represent the same physical configuration of the same field strengths. This is exactly analogous to what I described in linearized GR, where there was 2 different H and H prime, and that gave rise to the same Riemann tensor. Outside sources, we can turn off this term because there are no charges here, and we can impose, because A is not unique, and the potential is not unique, to make the potential well-defined or unique, we can impose a condition which is called the Lorentz gauge, which is the 4 divergence of the potential vanishing. And so this term will go away because the 4 divergence is taken to 0. So this term goes away and this term goes away, and we are left with the wave equation. Okay, D'Alembert of A nu equal to 0. So each component of potential obeys the wave equation. So we have these are called electromagnetic waves. These are non-dispersive, that is, all components of frequencies travel with identical speed, and they're transverse, and they move with the speed of light. So this is how Maxwell identified light as a fluctuation of electric and magnetic fields. Just like in GR, Lorentz gauge is an incomplete gauge fix, and we can still perform residual gauge transformations, that is, change A mu to A prime of mu, which is given by A mu minus 4-dimensional gradient of chi, such that chi satisfies the wave equation itself, so it's a harmonic function. Then we can see that both A and A prime will satisfy the Lorentz gauge condition. And you can count the number of degrees of freedom, just like we did for gravitational waves, or number of polarizations. To start with, we had depolarization corresponding to d component of A mu. Then we remove 1 because of the Lorentz gauge condition, so -1, so d minus 1. D to start with, and then 1 minus 1 from Lorentz gauge. And then there is still a residual gauge with a harmonic function, so that will remove 1 more degree of freedom. By removing a degree of freedom, I mean it can be either be set to 0 or be determined in terms of the rest of the others. Okay, so d minus 1, 1, which is d minus 2. So the number of polarizations in d dimensions for electromagnetic waves is d minus 2. Now let's get back to gravitational waves. To fix the gauge completely, we have to impose a further D conditions by performing D different general Fourier transformations with different morphisms. And actually not D different. I mean, what I mean is that D independent functions. So we can ask that the mu or the gauge fixed metric perturbations or phase reverse metric perturbations satisfy these conditions. First is that the phase must vanish, and the second is that the zeroite component of the phase reverse metric perturbations also must vanish. Okay, so these conditions are called the transverse traceless gauge. The nomenclature is obvious, and this is analog of the Coulomb gauge in electrodynamics, where you set instead of S0, you set A0 to 0, and instead of the trace vanishing, you set this to be 0.